Hi, this is Brian Fogarty, and this is a video for Chapter 12 of the book Quantitative Social Science Data with R, second edition. In this video, what we're going to do is look at the normality of residuals assumption. So, as I discussed in the chapter, this is not part of the Gauss-Markov theorem. It's sort of an extra additional assumption. And this assumption, if we meet it, or if we do not violate it, means that we're more confident in making inferences to the population from our data if our data is a sample. So some people don't even look at this because they say it's not as critical, but it is an assumption that's made. You know, one of the things that there's a bunch of assumptions in here, right? Everything has assumptions, I suppose. What I included in the book is ones that I think are commonly looked at. I've seen econometrics textbooks where they have anything from just the 4 Gauss-Markov to ones with like 11 or 13, and that's really a lot of that stuff is very pedantic, and so we're just trying to get at what people actually look at, and even still, people often just focus on really heteroscedasticity, and maybe they'll check some other stuff. All right, so let's look at how to test for normality in R. And first thing we're going to use is a histogram that we looked at previously in chapter 8, but this time it's a histogram of the residuals. So we are going to use a function that is gg underscore res hist. This is not sorry, res hist. You can see what I included accidentally there. It's good to know how to spell. And this is from the lindia package. All right, so we're going to include in the specification model 1, which is our regression model that we've been using. Okay, so model 1 plus, we're going to include this theme again, theme BW. If you remember the previous video, we got an error, or it wasn't an error, it was like a warning about the space. Hold on, let's see if it happens again. Okay, this just yells at us saying like the bin width is terrible. That's fine. That's fine. That's just our sort of ggplot default telling us that. Okay, so I'm gonna come here. I'm gonna drag this to make this bigger. All right, so we're looking at this. We're looking at the residuals. See, like, do they follow a normal distribution? You know, a normal distribution is the bell curve shape, right? That we all are familiar with. In truth, here, this is pretty good. So the thing that's a problem is we can't really even see it, but there's some residuals out here that's skewing the data. But if we just ignored that, like, this is pretty good for using real data. But okay, yeah, it's not perfect. Very much a judgment call. So that's what I mentioned in previous videos about, like, some people like to use just visualizations. I like to combine visualizations and formal tests just because I don't trust my own judgment or my own eyes to be like, yeah, that's definitely this or that. All right. So that suggests, you know, it's not perfect. Might not be a problem, but there's this big tail. Okay. So the next thing we're going to use is something known as a QQ plot, and this looks at, it compares what a theoretical normal distribution would look like with the residuals, our residuals, compared to what they actually are. So let's, the function here, this is again using the lindia package, is gg underscore QQ plot. We're going to do model 1 again, and we're going to add the black and white theme. So theme underscore BW. Okay, so let's highlight that, run that. I'm gonna click zoom and then drag it to make it a little bigger. Okay, so this red line is what the theoretical normal distribution should be. So if we're completely matching on it, like it's completely perfect normal distribution, then all of these dots will lie on this line. The more you have off of the line, the less likely it is that you're meeting the assumption for normality. It's very rarely the case that you will find residuals all on this line. Usually they're coming off of it in some way or another, usually at the tails. And that's what we see here. We also see like this one giant one up here. So this suggests we probably are violating normality. Okay. So as I said, I like to do a formal test as well. There is a standard one that's used, is known as a Shapiro-Wilk normality test. The problem is that it can only go up to 5,000 observations. Honestly, I don't know why. I mean, mathematically, I'm sure there's a reason. I just never looked into it. I find it just weird. Like, no, that's too big. So we need to do an alternative test. There's lots of them out there. We're going to use one known as Anderson-Darling normality test. So to do this, we need to load a package known as nortest. All right, we're going to load that. And then the test, the function is ad.test. And then we're going to do model 1 and then $residuals. So our model, our saved model, has stuff that it saves, and residuals are one of them. So if we look at names, let's do names model 1. So this tells us everything that's saved with our model object. Okay, so residuals is one of them here. Okay, so the null here is that the residuals are normally distributed. So let's run this test. Okay, so again, we're looking at the p-value. If it's 0.05 or smaller, we reject the null of normally distributed residuals and conclude that we do violate the normality assumption. So here, yes, it is below 0.05, so we have violated normality. Okay, what do we do? So there's different things we could possibly do. One way, we could use a different model. Instead of using, well, that's linear regression, we could use a different version. Some researchers just log the outcome variable. Again, that will have to depend on what that variable actually is. Another thing we could do is use a formal test known as a Box-Cox transformation. And this looks at whether and how we should transform our outcome variable to correct for normality. Okay, so we are going to use a function called powerTransform. And this is from the car package. So what we're actually going to do, we're going to do summary, just so we can see the results so they get printed out. powerTransform. Okay, so a lot of the functions from the car package, if it's multiple words, they'll uppercase the other word. So just be aware of that. powerTransform and then model 1. Okay, so let's run that, and I'm going to pull this up just because it's a little bit bigger. Okay, so a bunch of information comes out. What we are really looking at is this bottom part here. Okay, so this is likelihood ratio test that no transformation is needed. All right. From this, what do we conclude? Okay, we're using 0.05, so this is above 0.05. So what do we do? What do is we jump up and down because we didn't violate it. All right, so because if this is the null, we can't reject that, right? Using the 0.05. All right, let's say that we can, or let's say like, oh, I don't know, we violated it. We saw that before with our various tests, so we know we're violating it. The problem is this here, this EST power, with estimated power, this tells us what we should transform it to in order to fix the problem. So this is 0.95, which is essentially 1. And in fact, this column here, these print really weird. Rounded power is 1. And so, raising anything to 1 is the same thing, right? So we can't actually, this would say, okay, so if you want to do it, here's the correction. Oh, wait, the correction is actually the same thing, or essentially the same thing. So we're left in this kind of weird position of saying, okay, we do violate it. We checked as one common solution using Box-Cox, but that says we shouldn't do it. So practically, we're in a position where we should just leave it. Because if we start, torturing it and everything like that, we could be in a situation where the fix that we include or what we do is actually making it worse in terms of big picture and trying to understand the data, get real sort of substantive meaning out of the data. Another thing that some researchers say is not to even worry about normality because it's not part of blue. And the central limit theorem applies. So just don't worry about it. Just chill out. What I discuss in the chapter, and I say generally, is we should test for it, see if there's a problem. If the correction is super easy, straightforward, then go ahead with it. If it's complicated or unclear in any way, then don't worry about it. All right, so that is it for this video. Thanks for watching. I'll see you next time.